Hey everyone, Mr. Schachter here to talk to you about areas in the plane, section 7.2 in our text. Objectives of this video to calculate the area of a region bounded by two or more curves. So keep in mind what we've been trying to do up to this point is to take any curve like this curve right here and to calculate the area of any region. So let's take a look at this region right here, bounded between the x-axis and the curve, and we could find out precisely how much area is in that region. What this section is going to allow us to do is to find the area of any region. Take, for example, this region right here, bounded by these three curves. Now, you don't have to actually draw this. We're not going to find this. I'm just using it to prove a point. We're going to be able to find the area of any region bounded by any curves. In order to do this, we're going to learn two different ways. The first way is to use a vertical rectangle, or a vertical strip, and that's going to look a little something like this. Now, each of these vertical rectangles has a thickness, which we call delta x, which is kind of like its width almost, and it has a height, which we call h for now. Now, in order to calculate the height of these rectangles, what we had to do is figure out, well, how big is this value? We call this one f of c sub k, which is just the value c sub k we're using, and f is the function. And we're going to take g, which is the lower guy right here. We use c sub k. I can fix it. No, I can't. I can't fix it. C sub k. And we subtract them. Because suppose this was 5 and this was 2. And I wanted to figure out how much distance is accumulated. It would just be 5 minus 2, or 3. And then we just multiply the height times the thickness, or the base. And that's how we get our area of our rectangle. And what we're going to do is we're going to squeeze in a bunch of these rectangles, and we're going to sum all of their areas together. All right, and it's going to look a little something like this. Suppose we have this picture here, and we're going to be putting our rectangles in here, okay? And we're going to draw them one at a time, where our upper curve is f, that's up here, okay, this is f, and our lower curve is g, down here. And we're going to find out the area of this rectangle, and then another one, so on and so forth. Now, it's important to look at how we're structuring our rectangles. Notice that when we draw a vertical rectangle, okay, the vertical rectangle is perpendicular to the x-axis. So what that means is that this delta x, this thickness, is actually parallel to the x-axis. All right? So the delta x is on the bottom, and the height is on the top, from this to this, the top curve to the bottom curve. And we're going to use this idea of top minus bottom. Top curve minus bottom curve. All right? We're going to stick that idea in our heads whenever we're doing a vertical rectangle. That's really messy. Vertical. Okay, cool. So what this thing's going to look like in the end is, picture this. This is just one rectangle looked at a little more closely. You've got delta x on the bottom. You've got f of ck minus g of ck, which represents the height from the top curve to the bottom curve. Okay? And then each of these are going to be added up infinitely. You're going to have an infinite number of these partitions. But more interesting, you're going to make this delta x value go to 0. Make delta x go to 0. And by doing this, we're going to achieve the integral of a to b of f of x minus g of x dx, where f of x is the top curve and g of x is the bottom curve. Okay? So in general, the area between two curves, if f and g are continuous, with f always being larger or equal to g, then the area between those two curves is the integral from a to b of f of x minus g of x dx. Sometimes it is easier to write this expression, or this integration, as the integral from a to b of f of x dx minus the integral from a to b of g of x dx, using our sum and difference rules of integration. It depends on the curves. If the curves are easy, you might not need to. If the integration is a little more complex, then you might find you want to split up the integration. All right? Everything we've talked about so far has been with a vertical rectangle. When you're doing a vertical rectangle, your rectangles look like this. They have a top and they have a bottom curve. Okay? So top and a bottom curve. Everything in vertical rectangle land uses x values. All right? That means you use x bounds, you use x's inside your functions, and you use a respective x. However, you can also do these problems another way. And that is to instead draw your rectangles parallel to the x-axis instead of perpendicular. You can draw them like this. And you'll notice that these rectangles don't have a top and a bottom anymore. They have a right curve and a left curve. And we'll get into a little more detail later, but what I want you to understand right now is that whenever you do a horizontal rectangle, you must use y values for everything. Y bounds, y values inside your functions, and then y as a respect. The moral of the story is you can do most problems either way, but there's always going to be an easier one to pick. And the more practice problems we do, the better you'll get at finding which rectangle would have been the easier one. Let's try an example. Example 1 says to find the area of the region bounded by the curve y equals x squared minus 4 in the x-axis from -2 to 2. Show old way and the new way. Before we get started, let's draw a picture. So this is a pretty easy curve to sketch. It's just y equals x squared minus 4. So here's parabola. It has roots of -2 and 2, a y-intercept down here at -4, and so this parabola looks a little something like this. And since we're trying to find the area between the x-axis and the curve from -2 to 2, it's this region that I'm trying to calculate. I'm trying to find this. What is the answer to this question? Well, we can do this the old way. The old way of integration, right? We've been trained to do this. This is very easy because it revolves around the x-axis. So the answer to the question is just simply the integral from -2 to 2 of the curve x squared minus 4 dx. And I'll put this in parentheses. Okay, and you can use the fundamental theorem part 2, but I assume you guys will be fine with that yourself. We could try it ourselves on the calc just to save the time. So math 9, -2 to 2. And the curve is x squared minus 4, respect x, answer -10.6, which is what, -32 thirds? -32 thirds. It's not a shock that we got a negative answer because we found the region below the x-axis. And integration takes into account negatives, right? So that's okay that we got a negative answer. Let's compare this to the new way of integration. So the new way of integration states you're going to drop a rectangle inside, a bunch of them. And what I usually do for these problems is I like to draw just one rectangle. So I'm going to do a vertical rectangle, all right? And the top curve is right here. Well, the top curve is this curve right here. Well, the question is, what is this as a function? Well, this is just the x-axis, which is y equals 0. So this is going to run the integral from -2 to 2 of the top curve, 0, minus the bottom curve. Well, the bottom curve's down here. And that's just the parabola itself. The parabola itself is where the bottom of all these little rectangles would be. So the parabola itself is x squared minus 4 dx. And we know 0 just goes away, and I can take the negative and remove it from the integral, giving me this right here. Now you'll notice that the expression right here and the expression right here are nearly identical. The one difference is that you have a negative out front of the right expression, but the left expression does not. That's because this new way of calculating area is doing just that, calculating area. And we know that area is never negative. So this new way of integration will always give us the positive result, taking area into consideration as always being positive. So this is going to spit out an answer of 32 thirds. The same numeric value, but this time the positive version of it.